Yep. Okay. Hey. Hello, everyone. Yeah, I'll be talking about substrate storage. I'll be going pretty deep, explaining how it works, what it means to you as a runtime developer, and hopefully maybe answer some questions which are not fully understand about the structure of the substrate storage. First, I'm very aware that I talk quite fast, so I leave it to the front of the audience to start waving their hands if I start going a little too crazy, okay? Yes, just like that, perfect. But yes, there's a lot to cover, and so let's get started right away. First, let's talk about the abstraction of substrate storage. So you all are probably most familiar with this runtime storage API level. This is the declare storage macro, things that you most commonly use, but there's a lot of things that go underneath, and this is kind of what we'll be covering over the course of this presentation. But let's kind of go one by one and try to understand these different pieces at a high level. First, the runtime storage APIs. So there's a crate, SPIO, which can ultimately write to these other parts of storage given some key and value. You can actually use this SPIO crate directly, but we provide a bunch of easier APIs through the declare storage macro. So we have this very friendly way for you to define these maps and storage values and double maps. And these are the kinds of things that are generated automatically with the declare storage macro through the SPIO crate. Then we have this overlay change set. I'm not actually sure how many of you are familiar that we have this, but it's basically an optimization to avoid consistently writing and unwriting data from the database. So whenever you use a module and you query a storage item or you want to change a storage item, first, actually, it checks if the value is in this overlay change set. It's kind of this cache. If it doesn't exist, it'll go all the way down to the actual database, pull the value up, but then additional changes or reads will happen at this overlay change layer. There's two kinds of changes in this overlay change layer. There's this perspective changes, things that may happen. So there are things that we don't know we should actually commit to the database yet. And then eventually there's some state that we know we will commit to the database at the very end of a block, which is the committed changes. And again, ultimately these overlay changes are actually committed to the actual database once per block. So when you're doing multiple reads to a value across multiple modules, all within one block, it's all actually happening in this overlay change set. Then we have a Merkle tree. This is also known as the HashDB, and this is implemented in this crate Parity Tech tree. It's basically a data structure on top of the key value database. One of the things I'll be iterating over and over here is that this tree structure is actually like a virtual tree structure. That makes more sense later, but basically we support at this level arbitrary key and value lengths. The nodes here can be branches or leaves. And again, we'll kind of go deeper into the whole trie structure later. And then finally, at the bottom, we have this key value database itself. This is the thing that's ultimately implemented with RocksDB. It is basically some hash to some arbitrary byte array. And in Substrate, we use the Blake 2256 hashing algorithm to generate the keys here. And this is the literal database. This is the literal storage. So at the core of it in Substrate, you have just one table with some key and some value. But the abstractions above it is what makes it kind of the API that you all use. And that's kind of what the story I'll be telling as we go through these slides. Cool. So again, I'll reiterate this over and over. There's two kinds of keys. There's a tree key path, and there's a key value database key hash. And we'll hopefully explain that with some visuals. So Substrate uses a base 16 Patricia Merkle tree. So what do these things mean? So let's break it down one by one. A Merkle tree. Well, this is a thing you might be very familiar with in the blockchain space. It's basically some kind of structure to allow recursive hashing so you can get a fingerprint of the underlying storage. So you have some data, you hash that, you take two of these data hashes, hash that, take two of that hashes, hash it all the way to get to the top. And this last final hash is literally a unique fingerprint for all the data underneath it. Merkle trees allow you to more easily prove that some data exists within the tree with a Merkle proof. And again, we'll go back into that a little bit later. But this is something that, if you're in the blockchain space, pretty familiar with, hopefully. Then we also have a Patricia trie. This is a special kind of structure where basically the position in the tree defines the associated key. So you can see here, there's going to be a key like parity. And if you want to navigate that tree path, you follow the path, so parity. Or you can follow the path party and see that it shares nodes where it has common elements, there's common prefixes basically. And through this, you can generate actually a pretty efficient way to navigate these kind of arbitrary length key paths where there might be a lot of shared prefixes. Does this make sense, right? Cool. Finally, all the pictures I showed you there were binary trees. It's way easier on PowerPoint to just do 2 lines. But of course, all of these data structures scale way beyond binary trees. So in Substrate, we use a base 16 tree. This is really nice because one part of a hex character, a nibble, is a value between 0 and f, which is 16 characters. And so yeah, everything just works the same. It's just scaled up. So we take the best of the technologies, we put them together, and we get this base 16 Patricia Merkle tree. So let's get visual. What does it actually look like? So first, I'm going to show you kind of some of the pieces here. These are individual pieces that we're going to be showing in the next couple of slides. Again, there is a literal key value database here. This is actually something that is not going to be shown very much because I can't fit everything on one page, but know that this exists, and this is what we're using is the actual database. There's the different kinds of nodes we support. In the Merkle trie, you have these leaves, you have branches, and you can see branches can have values or no values, and we'll talk about that a little bit later too. We have a virtual trie table, so this is the actual keys that you might be most familiar with, the things that you're actually using. And of course we have a node structure. The actual node of a trie has these different components, like the header, the key, the children, and some value, okay? So this is the lay of the land, and now let's look at a very complicated graph. This, okay? So what we're doing here is we have this tree key path table, and we basically want to see what does that visually look like. It looks like something like this. Let's kind of walk through it. So first you can see that all the different nodes at the very end here are represented by these individual nodes here. Right? Great. Next you'll see that nodes with a shared path are the children of a branch. So all of these nodes here with the tree key path, they all start with A7, and therefore the beginning of our little pathway here is going to start with a branch with a partial value of A7. Then we want to progress and navigate through this tree, and we'll do that basically by following the children and just kind of following the tree path itself. So if we want to get to this leaf 0, 0, the next character is 1, we go to child 1, and we'll be able to find it, right? You'll see that when we follow the path, if, for example, this first one, node, leaf 0, 0, it ends, there's no more children underneath it, we get to the final node, the leaf itself. But you'll see actually that this line I'm drawing here, this is a key value database lookup. This is the thing I'm not really showing you well on this picture, but what we're actually doing here is looking up, querying the key value database to actually find where to get to this node. And I'll explain that a little bit more later, but you can follow the tree. You'll see here these middle 3 here, they all have a shared path of D3 next, right? So what do? We hit another branch. But this branch is a little bit different. This branch has a value, right? And so this is really important. Because we allow arbitrary key lengths in Substrate, we must, of course, allow for branches to also have values. Because we want to set a value at this path, but we also know there's children underneath it. So this is pretty unique. And then, of course, we keep going, and you reach the end when there's no more branches. That mostly makes sense, right? Awesome. So what did you just really see? Well, you saw that Patricia provides this tree path. You can go and navigate, follow the partials, the children, keep going, and ultimately generate a tree path to your data. And then Merkle provides this recursive hashing, right, of the children nodes into the parent. So what we actually do is we take this node. This is basically some serialized object. We hash that whole node object together with the prefix, with the key, and with the value, everything, and we get some hash. And that hash is where it will exist in the key value database. We, of course, take that value, put it into the children, and then hash that. And this recursive hashing is where the Merkle part of the structure comes from. And so ultimately there's 2 kinds of keys. This is the big takeaway. There's 2 kinds of keys here. There's the tree key path, which is set by you. This is something like the code. This is where the WASM blob for the runtime is stored. And you have full control over the arbitrariness of the key, the length, all that kind of stuff, right? And ultimately this key is encoded into the tree node as part of this key, the prefix, or the final end path, all that stuff. But ultimately you hash this whole tree node, get a hash value, and this is the value on your actual database. So if you were actually to query the database file on your computer, you would need to know the hash value of the tree where you want to go and get the node content, right? Okay. But wait, there's more, of course. There's child trees. So child trees is like kind of a extra level of abstraction or kind of a cool feature that you can implement here. Basically, we have our normal state to be tree, great, and then we can actually have a leaf node where the value itself is some hash, which leads you to the beginning of a brand new tree, right? And so what's cool about this child tree is one, the data here is kind of isolated. So anything in your child tree only affects it is inside of your state DB. So changes to child tree will be represented in the final hash of your state DB. But you can also track changes within just the child tree itself using the child tree root node. And also you can implement your own kinds of trees. You don't have to use our base 16 partition Merkle tree. You can implement your own kinds of trees starting at the child tree level. So this is a really useful abstraction, one that we use in both Substrate and Polkadot. We also have a prefix tree. This is similar to a child tree, but the API isn't quite as good. But you can see here a prefix tree is basically some kind of virtual tree where you start at a point where all the elements share a prefix, and then you can of course find all the elements with that prefix. This is actually something that's temporary, and I think ultimately these will all be represented as child trees in the future, but we actually have some pruning issues within Substrate that we're still looking to resolve. The reason I talk about prefix trees though, is because this is actually what is being used right now with the runtime storage. And this is actually new since the last Sub0. It's actually quite new in general. But if you're very deep into the storage already, you may be familiar with the fact that we take things like, when we use the declare storage macro and we generate for you these tree key paths like automatically, what we actually do is we take the module name, the storage name, and do some hashing stuff. Before we used to hash the module name and the storage name together in one hash. But now we actually separated it out so that there's actually individual prefixes for your data. So now when you generate some storage items for a module, all of your module's storage items will be under one prefix, right? And eventually it'll be under one child tree. And this is really awesome because you maybe migrate storage for a module knowing that all the stuff about this module stayed the same, even though your overall state tree might have changed. That makes sense, right? Cool. Okay, so let's talk about pruning. So pruning is another thing. Maybe if you're a validator or you've ever run the CLI, that you might have this pruning flag on, right? So pruning is meant for, is this process meant for holding older block states and cleaning it up. So we have this, this block 42, which has this root hash, and we go all the way down, this is a full tree. And let's say we want to update these two values of this tree at the very bottom. So what we're going to do actually is we're not going to recreate the whole tree in our database. That doesn't make sense. What we're going to do is just going to create a new, the new values and generate all of the nodes we need to get up to it. And the root hash can still refer to the old values. So what we're really doing is we're creating new database entries, but keeping the old ones too, and only creating database entries of the new things we need, right? So starting at block 43, I can start with this root hash. It'll point me to the old data, which hasn't changed, but also point me to the new data. And of course, we can continue to do this for another block, a new change. And eventually, what we do is we prune the old data. So you can see here, we just, when we want to clean up block 42, we just eliminate the parts which aren't being used by the other parts of the other blocks, the other parts of our storage. Another thing you can do actually is pin data. So similar to pruning where it cleans up data that's not being used, you can actually say, I want to pin this data. Even if it's not being used, even if it should be cleaned up, I can actually keep it in my database. Cool. So let's talk about Merkle tree complexity. This is an important part of when you're actually doing development, kind of what you need to keep in mind. First, reading data is not so great in a Merkle tree. It's O log n reads, whereas a normal database is something like O of 1 reads. So this is really not so great. You need to obviously traverse the whole path to get to your final value. Writing data is even worse, honestly. It's O log n reads, O log n hashes, and O log n writes. So you need to basically go here, read to the path of the value you want to change the value, hash the value, write the value, go up, hash the value, write the value, go up, all the way up. This is very expensive for a database. So why do we even use it? Like it's bad for reading, bad for writing. It's great for light clients. This is the important part. Substrate is a light client first platform. And it's really important to achieve a decentralized, trustless world, right? And so when you want to do things like Merkle proofs, you get really great performance in a light client. You only need O log n amount of data, basically, to be able to prove that some value exists within this tree. So you have something like a light client says, hey, prove to me this data exists. I know the root hash, and that's pretty much all I know. A full node will be able to traverse the path, collect the data, send it over, and then the light client only needs to do like, O log n hashes basically to verify, yep, this data and all this value you sent me does match the root hash that I know is correct. And this is really great. So we basically take all of the extra complexity onto the full nodes to make the light client node world better. So best practices. So you as a runtime developer, what should you be doing in general? So I think the first thing I want to say before I show you any of these slides is that you as a runtime developer are empowered to make decisions. And that is important. And you may decide, I want to break some best practices. That's probably fine as long as you're being conscious about the decisions you're making. And you have to be conscious about the economics and basically the impact you have to your network. But I think I can still give you some general best practices and see how you best want to apply them. So first, the fundamental goal as a runtime developer is for you to minimize the amount of storage your runtime uses. And so how do you do this? Well, you should only store consensus critical data in your runtime storage. You should not be storing random arbitrary metadata, random strings, random things, only consensus critical data. And I think maybe a good check of this is like, if there's no point in your runtime logic where you read the data, well, probably it shouldn't be stored, right? Okay. So let's think about a scenario, like a decentralized blog, right? The runtime should be able to come to a consensus about the content of the blog post. I think we all agree here that, what blog post is there should be known. But you don't need to store the entire text, right? You could do something like use IPFS. You could store the text on IPFS, receive a unique hash, and store that hash on the blockchain. You're able to achieve the same consensus-driven approach, but not having to bloat your storage with unneeded actual metadata information. Okay, so let's talk about structs and multiple values. So basically, you make them to a point where you need to decide whether or not you need to use a struct to combine a bunch of data, or you want to just separate everything as multiple values. Well, first, it's kind of important to understand the direct cost and indirect cost of just making a decision to add more nodes or less nodes to a tree, right? So there's direct costs of basically increasing the number of reads and writes to the overall tree when you add more nodes, right? Each one is O log n, where n is the number of nodes in the tree. And there's some indirect costs, right? Like the size of the value. Like when you have a larger struct with a lot of value, it just takes longer to read that value. So in general, the best practice is if you can store a struct. We know that it will cause less reads and writes to update multiple values, especially if these values are all being used together. So here, adding small items into large items when they're both accessed and you use at the same time is basically free in terms of these read operations. And then of course you create less overall nodes in the tree. But if you use a struct, there are some downsides too. Like it's less efficient for storing a single value. So if you have some big struct and all you want is this one piece of information, you have to load that entire piece, that entire data. It's not as efficient if you know that you're always accessing one piece of data kind of individually. Additionally, upgrades to structs require storage migration. There's kind of a well-defined structure for storage, and if some later point you want to update the storage, have more items, less items, or kind of just change things around, your blockchain is not going to understand how the things are currently encoded in your storage. So you're going to have to migrate that data over to be able to continue to use it. So these are the kind of decisions you need to make when you actually use a struct. But if you can, and this is what we do a lot in Polkadot and Substrate, is try to combine data that is relevant with one another into these structs. And this is basically optimizing the number of nodes you have in your tree. Okay, so you can also, using our friendly APIs in the declare storage macro, define the storage tree path generation. So here's an example of what you would write in your declare storage macro for a double map. And you can see actually you're allowed to implement different hashing algorithms depending on what your needs are. So if you define something like this in your code, the actual final tree path will be this, the hash, again, we did prefix hashes here. So hash of the module concatenated with the hash of the storage name, concatenated with the hasher you choose on key 1, and then concatenated with the hasher you use on key 2. Okay? And so what hashing algorithm should you use for generating these tree paths? Well, by default, again, I think I said it here, by default we use Blake 256. But Blake 2 is a cryptographic hashing algorithm, but it's quite slow. But it's important to use this kind of hashing algorithm when the user can influence the input of your hash. If you know the user cannot influence the input of whatever you're putting in this hashing algorithm, you can use a non-cryptographic but very fast hashing algorithm like XXHash or 2x. And this is really useful when you, the runtime developer, controls the value. So let's take a look back at one more slide. So you can see here, in the case where you control the module and the storage name, that's you as the runtime developer, you can use 2x. You're not a malicious actor. You're not going to be messing up your own storage. But if you have a user allowed to basically set these keys over here, they could mess up your storage, and I'll show you how. Basically, they can cause you to have an unbalanced tree. And again, this is impossible if the user can influence the path. So if the user can mess with these key values, control where in the tree that they put their, where the tree, their node exists, you can basically create these unbalanced trees. And basically what happens is you lose the properties of your operations being O log n. That if you go down this path, like the overall total number of nodes here, if you go down this path, it's going to be one different type of complexity than if you go down this path. And this is going to be really bad for your database if the user is able to attack it. Additionally, if a user really has a lot of control over where they can put their key in this database, they can actually place their node underneath some other heavier node, right? And this means when you have to do Merkle proofs and you have to submit the data to the light client, you need to submit this heavy item. Imagine putting a storage item underneath the WASM of your runtime. That means every single light client proof using a node underneath it would have to include this WASM blob. And this is really not good. So not allowing your user to basically mess up your storage is important. That all of these properties that we have about the storage is assuming that there aren't attacks on this tree path generation. Great. And so let's talk about lists. So lists is another common thing that people need to include, and I think it's a little bit confusing how exactly to use lists correctly in your runtime. So you can store a single value storage item with a vector. This is great for storing a bounded number of values. And it's really good when you need to basically change or access multiple values at the same time, and it enables iteration. So a good example of this is like the current validator set. We know that the validator set is fixed number. It's not going to be arbitrary length. So if we have a loop over the validator set, we know that it will be within some certain constraints or bounds, right? And we want to access necessarily the validator set all at once. We want to know who all the validators are kind of as one operation. We also have maps, which are good for storing an unbounded number of values. And it's good for random access. So we use this for user balances, like the amount of money they have in the balances module. And we don't know necessarily how many users are going to be on our blockchain. We don't know if we go under like a Sybil attack where basically you spam the millions of accounts with no balances in them. So we don't know necessarily how many values are going to be in this map. And also we know that we're not going to necessarily access data together. When I access your balance, I don't really care about anyone else's balance. I'm not accessing multiple users' balance at the same time necessarily. So it makes sense to separate things out, use this map. Finally, we have this linked map. And linked map is honestly a trap. It's this kind of thing that we provide to you, and you should be very careful how you use it. It really only makes sense to use a linked map if you're storing an unbounded amount of data, like a map, but your UI or off-chain worker needs to iterate on entries, not you. So again, what's really important in your runtime is that you're not iterating over unbounded data. You cannot create a wait function. You cannot create security around your runtime logic if it's unbounded and you have some kind of loop there. So really, this linked map is really more of a implementation deal for kind of this off-chain UI stuff. An example of this is the list of nominators and their nominations. So we don't know how many nominators there will be on a platform. We don't know their nomination information. And within the runtime itself, we don't really care, to iterate over all of it. But the UI definitely cares who are all the nominators, what are they doing. They want to show good information, they want to have easy access. And really this linked map, and I think this API will go away. Again, one of the things I mentioned here, we just moved to this prefix map. We will move to the child tree map. I believe once we actually have these things all as child trees, any map will be iterable. You will be able to go and use the API basically to go to the prefix you want where it has this map value and then just iterate over all the children. This abstraction really exists before we had these other things, but these APIs aren't quite fully up to date, and I think you'll see them continue to evolve. But these are the kinds of things to keep in mind when you're using different things. Yeah, so in general, the summary and takeaway here is that you really need to think about all the layers when you're writing to storage. When you're writing your runtime, it's not just like, bam, I'm just gonna put some value in there, no problem, just keep adding more, removing more, whatever thing I want. That you're working probably mostly in this runtime storage API, but it has ramifications and impacts to all the lower levels. And you really need to be conscious of that to be able to make the best decisions for your network. Okay, and yeah, that's what I have to say. Any questions?
Hi, that's very interesting, thank you. Have you looked at QP trees to increase the fan out to beyond 16?
Definitely, I have not. I do not even know what a QP tree is.
It's a Calcus. It means more than 4 bits. So it's like sparse arrays as each node, and then you can have I think up to 64 entries per node. So the depth of your tree will be much smaller.
Interesting. Okay, well, I can say this. I honestly haven't looked. I can give you the best informed answer I have, which is that one, the 16 base tree makes sense because obviously it represents a nibble, right? And we have these values represented in hex. Being able to access a nibble just by a single hex value makes sense. Additionally, we have this child tree structure where if there's something about your blockchain, which this is the perfect tree to use, I think you can implement it under this child tree notion. Fred has the mic, and he.
I can just say we have looked at sparse Merkle trees, but they're sort of research territory, and like this is an area that we know this works. We know what the implementation is, what the abstraction layers look like. We know how to work in this world. I think either sparse Merkle trees or some completely different accumulator is the way to go in the future. Like Merkle trees have a ton of problems, and you can solve them with things like RSA accumulators and a bunch of other structures. But like RSA accumulators come with a trusted setup, and sparse Merkle trees come with their trade-offs, and none of them have any like sound implementations in progress that I know of, at least. So it's a bit yes, but research.
Yeah, but I do think an important takeaway for everyone in this room is that we understand that what you might be building may not have the same assumptions that we have when we're building the rest of Substrate or Polkadot, and you might have some tree system that you really want to use, and we have the abstractions available to allow you to use these parts in the isolated parts of your module storage that you need. But I don't think, for example, all of our balances and all of our other modules will use our generic structure by default.
Is that, yeah. Can you elaborate a bit on what the child tree pruning challenges are?
Yes, I can actually. I learned this. Basically, I think right now, again, you remember that the hash of the actual database location is based on the contents of the try node, right? Let's go this one, right? So that you actually hash this node and you actually get the value of the database location. If you can have basically the null node, which has no values in it, and that will generate the same hash twice. And then you can have two different empty child trees basically point to the same database place, and this can cause problems. Like if for some reason that you clean it up, you basically get conflicts in this empty node space. Beyond that depth, I'm not quite sure, but that is the general problem that I think is being solved, that just basically trying to resolve any conflicts with where a child tree is being located. And I believe the solution is basically prefixing it with some kind of arbitrary prefix that you can define. So I want to have a child tree, and I'm going to define the beginning of the child tree with some unique value, like my tree, and then it'll prefix that in addition to avoid any type of conflicts between two different trees. But that's the best of my understanding in terms of what the current problem is. Yeah. And there are PRs available.
So maybe I'm confused, but you talked about the possibility of having a value on the branch and not on a leaf node. And it wasn't entirely clear to me why a value would end up on the branch. Because if you're hashing the value, you should get a full hash, which should take you all the way to a leaf node, I would assume.
Yeah, so this is the picture you're talking about, right?
Yeah.
Okay, so first we need to agree that there is arbitrary key path allowed in Substrate. So you will have a path which has this, which is a leaf node, and you will also be able to define a path which should have some value, which is a subset of this path.
Okay.
So we agree that there must be some kind of subset here which also has a value. And basically what we allow is through this prefixing, we can basically define like this branch with prefix 11 is different than this branch with prefix 10. This prefix 11 branch has a value. And basically when you go to this path here, you're going to be able to find the children, but you're also able to find the value of that path. So the reason why we allow for a branch to have a value is basically to allow this arbitrary path length.
But isn't doing that what allows for like the attack that you were talking about, where you could have something stuck under like a large data blob?
Right, but I think in general, that is a possibility of an attack, and it's something that you can avoid by doing other best practices about how you generate the tree key path. But the thing is, I think what the important part is that our layer keeps it abstract. If for whatever reason you have a decision to make, this path here, you can. You can also make your layer, again, let's go all the way back to the beginning real quick, that there's this SPIO, right? This is ultimately where you define the keys. And we generate the tree paths using that hashing in the declare storage API. So we actually will not run into this problem if you follow our API, but we leave it to you as arbitrary as possible to do what you want to do. I think it's kind of one of those things. It's a power. you can use it, you cannot use it. We provide a safe way to use it. If you choose to use it, you should be conscious about how you're using it.
Okay, so you can just shoot yourself in the foot basically by putting large data blobs at a branch and then putting stuff under it, and then your Merkle proofs are like gigantic and.
I think so, and we actually had a conversation with some of the other Parity devs about even ways you can optimize that. For example, instead of having the value in the branch itself, you could hash the value, have that be in a database, and have only the hashed value in the branch, right? And then of course all your branches would be like fixed size, fixed length. I mean, so you would avoid this kind of problem. But that incurs an additional database read. So I think you as a runtime developer, if you're brave enough to go into the Rust code, could probably even make that happen within the storage, but I think our current choice are based off the assumptions we've made about our own storage APIs.
Okay.
Make sense? We have a hand in the back, the very back.
I have two questions. First, I didn't understand how the child tree is different than a subtree. Like, if you just move what you draw.
The prefix tree?
No, child. Because you said when you update the child, the hash will come up to the main tree as well.
Yes. Let's look at this picture. Love pictures, right? Where was it? This one, right?
Yeah. So if you just had a space and you put it there.
Yeah. So basically, you have a child tree. You generate this root node, you hash it, and this hash value is placed into this leaf node. So as you change the child tree, this hash will change, this value will change, this node will change, and it will propagate all the way up to changes up here. So as you change the child tree, it will update this root node through this process. It's just different. This is a lookup, basically. This value is a lookup. Hey, a child tree starts here. And it just points you to a different part of your database.
If you would move it there instead.
Like if you actually put more nodes underneath this.
Yeah, because okay.
Yeah. So then you're talking about the difference between like a prefix tree and a child tree. So one, the important thing to remember here is that the child tree itself is some kind of interface, it's some kind of abstraction, right? And so the thing I mentioned here about the prefix tree is not being not having this same API. You can't get the root hashes because we basically haven't implemented a way in the API to just grab the root hash of any node. I think it's just I don't know exactly why we wouldn't implement the API, but we haven't. But child tree itself is its own kind of abstract object, and this is why you can actually implement your own tree structures using this child tree thing. If you started here, and then all of a sudden you were using a brand new tree structure, it wouldn't work. Your code wouldn't be able to traverse this half of the tree and this half of the tree the same way, right? But if you say, starting here, I'm gonna jump somewhere else and use a completely different abstraction, it makes sense, right?
Almost. Like you could have given the API, but underneath not be actually this.
Again, I think that a lot of the storage APIs will be changing. I think that I don't know the historical reasons why we just now moved to prefix trees, why we haven't been using child trees altogether, but there are some problems with the APIs, and I think long-term vision is everything will be child trees.
The second question, so when you put the for the pruning slide,
yes.
So there are like different value for the same key in the database, no?
No, actually, so this is all unique, right? So this root hash will be different than this root hash. So there'll be different values for the same tree path. That's correct, right? So the tree path will have different values, but its location in the database will be different, inherently because the value in that thing is different. So you must say, if I want to get this tree path information for which block, I want to get the tree path starting at block 43, I will navigate the tree path down, and I will get some value. But if you say starting at block 42, I will navigate the same tree path but get to a different point because these nodes represent different values.
So KVDB keys depends on the value.
Yeah. So again, the KVDB key is the hash of this whole tree node, which
Okay,
has the value.
Yeah, right.
Right? So really, every single node is unique. And when you're adding new values to your database, you're literally creating new database entries. Every single new value in this thing is a new database entry. And you navigate to that database entry using this tree path. Again, the tree path is a virtual table. It's a virtual tree here. Really, the only thing that exists is a key value database as a table. Right? This is the. Okay. We have one last question that I'm gonna stop talking.
So as a best practice, you recommended using structs over multiple values. Is there kind of a point at which that would no longer be true? Like, I mean,
Yeah. So
Otherwise, the logical extreme of that is like we have one struct and it holds all the data for our module.
yeah, and that is exactly this size of the value thing. So you should not be doing things crazy like that. Like if you're trying to access a single value in this big thing, it should be its own value. Like if there's logic which running this function will access this one value, that should probably be its own storage item. But if, for example, I have a kitty, right? And a kitty, I'm always going to be looking up like what is its owner and its ID and it's this. You could put it in a struct. Actually, in my upcoming kitties tutorial, I'm going to actually split it up because it's going to be, we don't have enough items in my kitty module to really, justify the difference between like, 3 items or 1 item. Like, n doesn't matter if it's 1 or 3 more, right? But at the overall level of your runtime, you really should make conscious decisions. Like, if I'm adding a new item to my runtime to like upgrade it, if I can put it into a struct, that'll be better. And there are times you see that we like shove some data into a struct just to optimize the fact that we always use this data with the context values around it. So again, this is kind of a decision you need to make your decision. It's hard to be up here and be like, this is what you should always do. Always use a struct, have everything as one struct. That is not the correct thing to do. But you have now the tools and the information to basically make that decision yourself. You should look again at the code you've written and figure out, okay, is this value being used in the same context at all the same times? Right?
Okay, so like if you had accounts and there was a lot of information associated with each of these accounts, they should probably be separate values as opposed to a gigantic lookup, a gigantic map.
If you have information about accounts which all is kind of independent of one another, yes, they should be separated. And if you think about it, we have all this different data about accounts, like whether it's a validator, it has some stuff in the validator modules, and whether it's just its balance in the balances module, we split it up itself. But if there's something about it, like being a validator, you have a bunch of properties that you that you want to update. Like how much commission do I want to take? Plus what is my whatever validator status, all that kind of stuff. Those things all get updated in a single function. Like it's like update my validator preferences, right? And obviously then we should have validator preferences be a single struct because we're always going to update it using one function in one time, right? We're always going to read it once, update everything, write it, and so it makes sense to make a struct. We have one more here in the front, or in the back. Wow, lots of questions. Storage is cool, right?
A simple question. Are there any plans for changing RuxDB to hyper-level DB or other new generation?
Yes, my understanding is that the abstraction layers we've built allows for you to swap RuxDB with another key value database. I think we as a Substrate or a Parity, we're not going to be like making that a friendly thing. Like I don't think we're spending any time being able so you can switch to whatever key value database you use. But I think RuxDB has the needs that we want. I mean, we've been pretty happy with it, I think, for what we're doing for our needs. But the abstraction levels, I think at a certain point, again, if you're brave enough, you can get in there, and I think it would be possible to change it.
Okay, we've got one more question.
Cool.
So can you talk a little bit about the difference between storage for modules and storage for smart contracts?
Yeah, so
particularly in the context that I hear that transactional changes to storage for modules is coming.
Right, okay, so the contracts module is probably the most advanced module we have in Substrate, and it of course allows for contracts to have their own storage, and these are actually child trees. We actually use child trees in this case. So for every contract, it will have its own child tree, and the data will be put there. So I don't know if I need to say more than that for your particular question, but really, when you're accessing the storage, and if you look at the code, we will use a child tree to represent all the storage items for all the different contracts in your contracts module. Is that enough, or is there maybe something more specific that I can attempt to answer?
So, yeah, as I understand it, storage for smart contracts is therefore revertible in terms of using overlays.
Right.
Mm-hmm. Whereas for modules, so far it's not revertible, but
yes,
transactional storage mutation would change that.
Yeah. So the overlay chain, this transactional overlay is actually, this logic is built into the contracts module. So Sergey himself has written all this code to be able to allow you to manage basically if the contract function failed, that it could get reverted and that isn't updated. And he does this by making some assumptions about what contracts have access to, I think, at the moment. I will say this, if you go to Substrate and you look at one of the PRs, there's a PR which is actually going to, which hopefully will enable this transactional overlay at the runtime level. So you'd be able to define saying, hey, this part of my code is going to be in the overlay, and at this part of the code, commit it. And this is something that ideally we'll get in there. I think there's been some kind of problems getting it merged because it's kind of a heavy change, but I think we absolutely know about this problem. I mean, we heard the last presentation that this is one of the complaints that we have, and we actually have a current PR right now with, I think, all green check marks that will solve this problem. And so if that's the case, then I think even Sergey will be able to remove his unique abstractions and basically use this transactional overlay for reverting the bad state changes for any type of transaction to the runtime level. Okay, cool, great. Thank you for your time.